Welcome to this explainer. Look, if you've been anywhere near the internet or reading the news lately, you are probably drowning in a total buzzword soup of AI terminology. Seriously, everyone is just throwing around terms like machine learning, deep learning, transformers, and RAG. But here's the secret. Most people using these terms don't actually know how they relate to one another. So today, we're going to untangle all of that. We're going to map out exactly how these technologies fit together, and then we're going to hold up a mirror to see how each one attempts to replicate the ultimate computer, the human brain. Here is our agenda for today. 1. Mapping the AI landscape. 2. Machine learning versus synapses. 3. Deep learning versus the visual cortex. 4. Transformers versus selective attention. 5. RAG versus memory recall. And 6. Teaching tools versus literal claims. Let's get right into it. Section 1. Mapping the AI landscape. Okay, so people often treat these four terms, machine learning, deep learning, transformers, and RAG, as parallel categories, right? Like they're all just different items on the same menu. And that is exactly where the confusion starts. In reality, three of these concepts nest strictly inside each other, kind of like Russian dolls. Artificial intelligence is the broad, overarching field. Tucked inside that, machine learning is the dominant approach. Deep learning is a very specific flavor of machine learning, and transformers are one specific architecture of deep learning. But notice RAG, Retrieval Augmented Generation. RAG is the odd one out here. It's essentially just a plumbing decision that bolts a search engine onto a model completely outside of this Russian doll stack. Section 2. Machine learning versus synapses. Now that we have our map sorted, let's hold up our mirror to biology, starting with machine learning. You probably already know the basic shift from explicit programming to ML. Instead of writing really rigid line-by-line if-then rules for something like a spam filter, we just feed the system thousands of examples and let it infer the statistical boundaries entirely on its own. The biological cousin here is synaptic learning. And honestly, this is probably the deepest, most honest analogy in all of AI. Think about how a child learns what a dog is. You don't hand a toddler a rulebook detailing exact snout length and ear geometry, right? No. Instead, they just see 100 dogs, and the concept organically crystallizes in their mind. The brain does this by tuning synaptic strengths. Connections that fire together get stronger, which neuroscientists call Hebbian learning. Well, machine learning does the exact same thing, just with math. It nudges numerical weights up or down to reduce error. Both approaches completely replace explicit, handwritten rules with experience-shaped parameters. But here's the crucial point where this analogy completely breaks down. Efficiency. Human brains are just remarkably efficient. We learn continuously from incredibly sparse data. A child might only need to see 3 or 4 dogs to get the concept forever. And learning what a cat is doesn't suddenly make them forget what a dog is. Machine learning models, on the other hand, require massive data sets, literally millions of examples. Plus, if you try to teach an ML model something new, it can suffer from what's called catastrophic forgetting, abruptly overwriting the knowledge it just worked so incredibly hard to build. Section 3. Deep learning versus visual cortex. Moving one layer deeper into our map, we find deep learning. Now, the word deep here isn't philosophical at all, it's totally structural. These models use literally stacked layers of simple computational units. The early layers catch incredibly crude features, like a basic straight edge or a single sound syllable, and then they pass them up to later layers to assemble complex meaning, like a recognized face or a full sentence. And this brilliantly illustrates why deep learning was built this way in the first place. It's not just a metaphor. It shares a genuine structural hierarchy of abstraction with the visual cortex in your own brain. Your visual system processes reality in distinct stages. The V1 area detects basic edges and orientations. Later areas assemble those raw edges into shapes. And finally, the inferotemporal cortex recognizes those shapes as whole objects and faces. A deep neural network does this exact same progression. Early layers act as edge detectors, middle layers find textures, and the deepest layers grasp the whole concept. It's pretty amazing. But the mirror cracks quite a bit when we look under the hood at the actual raw mechanics. While the high-level hierarchy looks similar, human neurons are vastly more complex than the simple weighted sum units sitting inside a deep neural network. Most importantly, the brain absolutely does not learn using backpropagation. Backpropagation is the core mathematical algorithm that makes deep learning run, calculating exactly how to adjust weights across all those layers. Neuroscience still doesn't fully understand how the human brain assigns credit for learning. but we know for sure it's not doing backpropagation math.
Section 4. Transformers versus selective attention.
All right, nestled deeply inside deep learning is the architecture that unlocked massive systems like GPT and Claude. We're talking about transformers. Their defining magic trick is a concept called self-attention. Instead of reading text sequentially from left to right like we do, transformers use parallel processing. Every single element in a sequence directly looks at every other element all at once, deciding exactly how much each part matters. Let's look at the biological equivalent because it's super relatable. Think about being at a crowded, really noisy party. There's music bumping, glasses clinking, a dozen conversations happening all around you. Then, suddenly, someone all the way across the room says your name. Boom! Your brain instantly reweights its focus, drowning out the background noise to tune right into that specific voice. That is your brain's selective attention at work. Well, Transformers' self-attention is that exact same move, just applied to language. When a transformer model processes a word like it dynamically asks, wait, which earlier words in this giant paragraph does it actually refer to, and assigns a mathematically higher weight to the most relevant ones. However, we need to be really careful here. Transformer attention is mostly just a brilliant naming coincidence dressed up as a deep truth. Biological attention involves incredibly complex real-world bottlenecks, extremely strict energy budgets, and, crucially, conscious control. A transformer's attention isn't conscious at all. It's simply a massive matrix of similarity scores being computed mathematically in parallel. So it provides a really useful intuition for how the model handles context, but it is super shaky as actual biology.
Section 5. RAG vs. Memory Recall.
This brings us to RAG, which, remember, sits entirely outside our nested Russian dolls. RAG, or Retrieval Augmented Generation, is a workflow built specifically to fix stale knowledge and those confident hallucinations we all know about. Step 1. You ask a question. Step 2. The system retrieves relevant documents from an external database. Step 3. It feeds those fresh documents right into the model alongside your question. Step 4. The model outputs an answer firmly grounded in those facts. Like we said earlier, it essentially bolts a search engine directly onto a frozen model. And the biological mirror for this? It is incredibly relatable. A standard AI model's training is kind of like your general semantic memory. It's a massive, hazy blend of facts that's hard to quickly update and sometimes impossible to precisely cite. RAG is much closer to just looking things up. Just like you pull out your phone to check your contacts instead of straining your neurons trying to remember a 10-digit phone number from scratch, RAG brings external pages into its working memory right alongside your prompt. Biologically, this is very akin to your hippocampus retrieving a specific episodic memory and feeding it straight into your prefrontal cortex for active reasoning. But where this analogy breaks down is in the sheer perfection of the recall. Human memory retrieval is a messy, highly associative, and reconstructive process. When we remember something, we are literally rebuilding the memory on the fly, which means we often rebuild it incorrectly. RAG, conversely, performs a rigid, literal database lookup. It pulls the exact text precisely as it exists in the external store, completely bypassing the messy, reconstructive nature of human thought. Section 6. Teaching tools versus literal claims. So now that we've mapped the whole landscape and tested the mirrors, what's the ultimate takeaway here? Well, the honest meta point is that brain analogies are absolutely fantastic teaching tools. They really are. But they are terrible literal claims. Modern AI is heavily engineered for what works efficiently on GPUs. It's built for math, not biological fidelity. Furthermore, AI very cleanly separates memory from computation, whereas in the human brain, there is absolutely no clean separation between the two. To really put the biological reality in perspective, just consider this one number. The human brain, with all its mind-blowing complex reasoning, continuous learning from incredibly sparse data, and pinpoint selective attention, runs on roughly 20 watts of power. 20 watts. That is literally the energy of a dim light bulb. Meanwhile, the AI models we've been discussing require massive, sprawling data centers consuming actual megawatts of power just to run their matrix multiplications. So, as you continue to learn and navigate this rapidly evolving field, absolutely use these biological parallels to build your intuition. They are genuinely helpful for wrapping your head around the concepts. But always remember this quote. If anyone tells you a transformer thinks like a brain, that's marketing, not neuroscience. Which leaves us with a fascinating and maybe even a little bit unsettling final thought.
We are building these incredible systems that can pass the bar exam, write complex code, and converse with us completely fluidly. But if these machines don't actually process information, learn, or think like we do, what kind of alien intelligence are we actually creating? Thank you so much for joining me on this explainer. Keep asking the big questions, and I'll see you next time.